All right, let's get going. So today we're going to talk about related rates and the whole linear approximation thing. And maybe a couple other things if we have time, although I don't imagine we will. Then Thursday, sorry about that, we're going to do exam review for your exam on Friday. Yeah. Before we do either of those things, I just want to cover one more derivative rule we haven't talked about, and that's the following one. The derivative of the arc tangent of x. Or if you prefer, the derivative of the inverse tangent of x. Those are the same function, it's just a different way of writing them. Some people like one name versus the other. I happen to like the first way of writing it personally because some people confuse inverse tangent with 1/over tangent, which it is not equal to. Just want everyone to be super cool. Inverse tangent of x is not the same as 1/over tangent of x. Because 1/over tangent of x is cotangent of x. Inverse tangent undoes what tangent does. So for example, we know, or we might know, that tangent of, say, pi over 4 is equal to 1, or tangent of pi over 3 is equal to the square root of 3. Inverse tangent undoes that. Interchanges the x and y input-output relationship. So the arc tangent, or the inverse tangent of 1 is equal to pi over 4. And the arc tangent, or the inverse tangent of root 3 is equal to pi over 3. It's very, very much like how exponential functions and logarithmic functions are inverse functions, or undo what the other one does. Okay. Back to the main event here. The derivative of arc tangent, or the derivative inverse tangent, is equal to 1/1 plus x squared. And of course, if you know a derivative of x, of a function of x, you know the chain rule version of it as well. So if you know the derivative of arc tangent of x is 1/1 plus x squared, then you could say the derivative of the arc tangent of x cubed plus 5 is 1/1 plus your stuff squared. And I said the magic word stuff, so I have to multiply by the derivative of the stuff. The usual pattern for chain rule. If you know the regular version of the derivative, you know the chain rule version of the derivative. Because replacing x with something more complicated, and then at the end, having to multiply by the derivative of that stuff. One more example, the derivative of the arc tangent, let's make it gross, of secant of x plus x to the 4th is going to be 1/1 plus all that stuff squared. Ooh, did I leave myself enough room? Maybe. Sorry, it's a little tight. Apologies. And then we multiply by the derivative of that stuff. The derivative of secant of x is secant of x times tangent of x plus the derivative of x to the 4th is 4x cubed. And yes, you definitely need parentheses around all of that. If you don't have those parentheses, it looks like the 4x cubed isn't multiplying all of that, and it needs to multiply all of that. So be liberal with your parentheses, whether it's chain rule or quotient rule or product rule, you need them so that whenever you're having like a derivative, you're getting all of the derivative multiplied by whatever it's supposed to be multiplied by. Okay, that's all. I just realized we hadn't talked about that last kind of particular derivative rule. I should mention there are other inverse trig functions whose derivatives can also be known. For some reason, we only talk about this one in this class. I don't know why, but you're not typically responsible for knowing the derivative of like the arc sine or the arc secant or any of the other inverse trig functions. For some reason, arc tangent is the one. I'm not sure why, but it is. Yeah. No. Oh, yes. Sorry. Good call. Thank you. I missed the square there. Yeah, we for sure need the square there. Should be 1/1 plus your stuff squared times the derivative of your stuff. Thank you so much. Yeah, I missed that completely. All right. Moving along, though, to the related rate stuff. Also commonly referred to, I don't call these just word problems, although they are word problems, because after these, we also do some other word problems that are different. But yes, related rates are one of the word problems, and they are typically kind of I don't know, the usual kind of hallmark of a related race question is they're telling you how something is changing and asking you how something related is changing. For example, numbers. Here's kind of a typical go-to beginning example. The radius of a circle is increasing at 2 inches per second. Oh, a rate of change, 2 inches per second. When the radius is 5 inches, how fast is the area of the circle increasing? So let's talk about the process for doing this. There's usually what I think it was like 3 or 4 steps. I mean 4 or 5. Usually the first step, depending on if it's necessary, is to draw a picture of the kind of shape or thing that, or situation that's happening. So here we have a circle. And we're going to label the things that are changing, or at least the things that make sense to label. So here the radius is definitely changing, right? It's getting larger and larger. I wouldn't write that the radius is 5, right? The radius is just some variable, we're going to call it r. And so there's my first step. Step 1, draw and label. Label things that are changing, or label the variables. It doesn't really make sense to label the area here. Like you could shade in the circle and call it the area, but that seems kind of silly, so I'm not going to do that. The second thing to do is to identify what is changing. And for whatever reason, math people seem to really like using the dy dx or the dr dt, or what's generally called the Leibniz notation for these types of problems. I can't tell you why. I just know that it was taught to me that way, and every math person I've ever seen do it ever prefers to use dr dt or da dt or whatever the da dx, whatever notation you're using. So that's what we're going to use because that's what people are going to expect. So what's changing? Well, the radius is changing. And we know the radius is changing at 2 inches per second. So we're going to say that dr dt, the rate of change of the radius with respect to time, is equal to 2 inches per second. I don't super care about the units, but I'm going to write them anyway. Well, let's see. They told me the radius of the circle is increasing at 2 inches per second. And then they also asked me, how fast is the area increasing? So I want to know how fast the area is increasing. So usually, although not always in these problems, I'm going to say the area is increasing, the rate of increase is dA dt, and that's what I'm trying to find. So frequently, there's going to be one rate of change that you know, and one rate of change you're being asked to figure out. Sometimes there's more information than that, but often it's this kind of situation where you've got one thing you know how it's changing and one thing you're trying to find how it's changing. Sometimes there's 2 things you know how they're changing, and then they ask you, but usually this is. So after you've done that, after you've identified what's changing, or as my old professor used to say, identify the d what's. The top thing is a d what, the bottom thing is a d what, usually a dt on the bottom, but not always. Then we want to find an equation relating the non-time variables. So we want an equation relating, in this case, area and radius. Most of the time, this is going to be some geometric formula, like the area of the circle, or the volume of the cone, or the Pythagorean formula if you've got a triangle, or maybe something else, but it's usually some sort of geometry thing. So in this case, it's going to be area equal to pi r squared. And now, after this, we're going to differentiate both sides. Now, I'm going to show you what we're really doing, and then I'm going to show you the way we're going to do it. So when we differentiate both sides in step 4, well, let me point out, area and radius are both functions of time, right? As time goes on, the radius increases. Technically, if I really, really wanted to, I could up here say something like the radius as a function of time is equal to 2 times t inches, right? At time 0, I'm pretending I'm starting off like where the area starts off at 0. And then after 1 second, the radius is 2 inches. After another second, the radius is 4 inches, and so on and so on. But we don't need that. So I'm not really going to use that. But I know that radius is a function of time, and so is area. So check this out. I'm going to rewrite this as area as a function of time equal to pi times radius as a function of time squared. Usually you're not going to do this, but I want you to see what's happening here. Then we're going to differentiate both sides. Sorry, I wrote that kind of small. The derivative of a of t is a prime of t. And the derivative of pi times some stuff squared is pi times 2 times that stuff to the first power. But I said the word stuff. What do I have to multiply by? Right, the derivative of the stuff prime, r prime, whatever you want to call it. But now, using the notation that we're actually going to use, what we'd actually write is dA dt equal to pi times 2 times r times dr dt. This is the same stuff. This is just a different way of writing. After you have differentiated both sides, you typically do the last step, which is to plug in what you know, solve for what you want. So usually you should be able to plug in for all the things that you don't, that like everything other than dAdt, we should be able to plug in for. Sometimes it's a little more work. Sometimes you have to do a little extra work to find something that's missing, but you should always in some way, shape, or form be able to plug in for all of the unknowns except for the one that you're trying to find. So here, step 5, plug in. Sorry, I should have said step 4, differentiate. Apologize. And finally, step 5, plug in and solve. So if I plug in, let's see, I know that the radius is 5 inches because they told me in the problem, and dr dt is 2 inches per second. I'm going to get that dA dt is equal to, I'm going to write this as 2 times pi because that's more normal. 2 times pi times r, which is 5 inches, times dr dt, which is 2 inches per second. If I multiply this out, I'm getting 2 times 5 times 2 is 20 times pi, so 20 pi. And the units end up being what they should end up being. Inches times inches per second, which is inches squared per second, which should be the units if we're talking about the rate of change of an area. Or if it was a volume, I should have gotten inches cubed per second. Or if it was a length, I should have gotten inches per second. More generally speaking, whatever unit of measure is, whether it's inches or feet or meters or yards or other miles, right? Per unit of time, seconds, hours, minutes, years. If it's a length, it's your unit of measurement to the first power divided by time. If it's an area, it's your unit of measurements squared per unit of time. If it's a volume, it's your unit of measurement cubed per unit. This won't happen on your test. If someone's trying to be a jerk, they might give you like different units. Like this is measured in inches and this is measured in feet. And you have to like do some. No, that's not going to happen on your test. But it could happen in like a homework problem, which is super annoying. But so this is the gist of how related rates work. Figure out what's going on, ask what's changing, get an equation, differentiate, plug in, and so on. And I don't usually write the units until the very end, although if you want to keep track of them, it's nice to see that the units in the end should work out to be the correct kind of unit for the thing that is changing. We can also ask for this one. We want to follow-up question. How fast, how does not start with W? How fast is the circumference changing at the same moment? Well, we have an equation for circumference. Circumference is equal to 2 times pi times the radius. And then if I differentiate both sides, just like with implicit differentiation, because literally that's kind of the same idea, that's why we talk about it first. The derivative of circumference is the derivative of circumference. And it's equal to the constant multiple hangs out. And the derivative of radius is the derivative of radius, or the rate of change of radius with respect to time is the rate of change. And then we plug in. There's nowhere to plug in the 5. Right? We said at the same moment when the radius is equal to 5, but there's nowhere to plug that in, and that's okay. Sometimes that happens. There are some problems where it doesn't matter at what moment you're doing it at. The things depend on each other in a purely kind of linear way, I guess is what I'm trying to say here. So dc dt, the rate of change of the circumference, is just going to be 2 pi times 2 inches per second. So that's what the r dt was, which ends up being 4 pi inches per second. Which kind of makes sense if you think about it, because the circumference is just a multiple of the radius. If the radius is changing at a constant rate, the circumference is also changing at a constant rate. Questions so far? We're definitely getting more examples, but let's see if there's any questions. Let's look at another example here. I have enough room. I have enough room. Let's use a different color though. Let's see. Okay, so the hardest part of these is sometimes they take forever to write out. So we'll write out the pertinent parts here. Gabriella is standing 6 feet from her sister Mia. If you know Grant, these are his children's names. Who is holding a balloon. The Grant is my coworker. Grant Acosta. Mia lets go of the balloon. And it rises at a rate of 2 feet per second. 4 seconds later, how fast is the distance between Gabriella and the balloon changing? And don't worry about the fact that they might be different. So let's draw a picture. So here's Gabriella, here's Mia. And Mia lets go of the balloon, which starts going this way. Up. Here's the balloon. So let's see here. We have some things that are changing, some things that are not. The distance between Gabriella and Mia is constant. It never changes. Things that are constant, you should just write down whatever number that is. In this case, that distance is 6 feet. On the other hand, the height of the balloon is certainly changing. And I don't want to give it a constant name. I want to say, well, that's going to be, you could use Y, you could use H, you can use literally whatever letter you're comfortable with. I typically use H for height. And then we also have the distance between Gabriella and the balloon, because we're being asked about. And usually for diagonal distances, I use the letter S. I don't know why, it's just typical. I'm going to call this S. People would use Y and Z maybe. I like H and S. It doesn't. All right, so let's read the problem and find out what we're given. So there's our picture with the variables labeled. And then we want to identify the D. So I guess this could be my, my part 1, and then part 2. I want to figure out what's changing. Well, let's see. I'm looking for the rate of change, and literally I see the words, the balloon is rising at a rate of 2 feet per second. So this length here is increasing at 2 feet per second. The dHdt is 2 feet per second. On the other hand, we're also asked, how fast is the distance between Gabriella and the balloon changing? So we want to know what dsdt is, but we don't. But we're trying to find. So then we're going to find, or try to find, an equation relating those non-time variables. Your equation is never going to have time in it, typically, until you differentiate this. So let's see. Well, I see a right triangle that usually means one of two things. Typically, it means Pythagorean theorem. Sometimes it means you're using like similar triangles, but usually Pythagorean theorem. So here, I can say 6 squared plus 8 squared equals s squared. And here's the really great part about this. You don't have to do any solving. You can just differentiate both sides right off the bat, which is nice. It's easier that way. So now we're going to differentiate both sides. Okay, what's the derivative of 6 squared? Right, 0, because it's just 36. So 0 plus the derivative of some stuff squared is 2 times my stuff times the derivative of my stuff. And the same thing on the right. The derivative of some stuff squared is 2 times my stuff times the derivative of my stuff. So I get 2h times dh dt on the left and 2s times ds dt on the right. Now, we're going to plug in and solve, but I will point out, what are we trying to solve for? ds dt here. So we're trying to solve for ds dt. We should be able to plug in for everything else. So for h, for dh dt, and for s. We actually don't know h or s. So we have to go back and find them. So let's see. We know that dh dt is 2 feet per second, and we are talking about 4 seconds after the balloon was released. So if it's been 4 seconds and the balloon is rising at 2 feet per second, then we know that the height is going to be how many feet? 8. Right? 2 feet per second for 4 seconds. 2 times 4 is 8 feet. And then you can either use the Pythagorean theorem to find s. You say, okay, well, I've got this triangle now. 6, 8, s, and I can say 6 squared plus 8 squared equals s squared. And 36 plus 64 is 100. So s is equal to 10. But I will point out, it's a maybe here. A lot of the times when these kind of triangles come up, people try to pick numbers that are nice. They are often going to pick something that's a multiple of a 3, 4, 5 right triangle. This is a 3, 4, 5 right triangle, just all the sides of it multiplied by 2. So 3, 4, 5 times 2 is 6, 8 times. You can kind of jump to that conclusion often if you want to, but it's less, I would say it's a less of a guarantee. So step 5, plug in and solve. We've got, I guess I could cancel the 2's here. That seems like a reasonable thing to do. Divide both sides by 2. And just say that h, which we said was 8 feet, times dh dt, which is 2 feet per second, equals s, which is 10 feet, times ds dt. Or what I would really do actually is say 8 times 2 equals 10 times ds dt, solve for ds dt, and get ds dt equal to 16 divided by 10, which is 1.6. And then I would just add in the right units. I know that ds dt is how a length is changing, so it's going to be feet per second. Which would have worked out, right? If I had done the division here, feet times feet per second divided by feet, one of the feet will cancel and you get feet per second still. So you can write the units in. If you kind of have an idea of what unit you're supposed to end up with, you can really just write that in at the end instead of trying to figure out writing all the units the whole way through. How complicated do we want to get here? Not that complicated. Cool. Let's look at another one. Good to practice these. It looked like, at least on most of the practice exams, she was giving you the equation of the shape that you needed to like find the thing often. So just something to be aware of that you may already, you might not have to know it. Let's look at the next one. Okay, the radius of a cylinder is increasing at a rate of 3 feet per hour. And the height is decreasing at a rate of 2 feet per hour. How fast is the volume of the surface, is the volume of the cylinder changing when the radius is 5 feet and the height is. Okay. Same 5 steps with maybe a slightly different flavor, but still the same 5 steps. The first step, we're going to draw the shape. Cylinder, looks like this. We're going to label the things that are changing. And in this case, both the radius and the height are changing. So the radius right there, height. And we're labeling them with variables because they are changing. Okay, so step 2. We need the equation. Oh, no, we don't. I'm skipping a step. Sorry, we need the things that are changing. So let's see, radius is changing. So we're going to say that dr dt, let's see, radius is increasing at 3 feet per hour. So dr dt is going to be 3. I guess I like to write the units, but you don't really need to. And then the height is also changing. The height is changing at 2 feet per hour. So dh dt is equal to 2 feet per hour. Y'all are gonna let me get away with it? All right. What am I missing? Right. So what should I say that dht actually is? Negative 2 feet per hour. So when you have a rate of change that's negative, it means exactly the thing is getting, or I should say, when you have something that's decreasing, it means the rate of change is negative. Or right, think about graphically. If you have a function that's decreasing, its derivative, aka its slope of its tangent line, is a negative slope. So negative rates of change should go with negative derivatives, or things that are decreasing should be going with negative derivatives. And now we want the equation of the, oh, I missed a thing. Kind of. I wrote down the things that I knew were changing, but I forgot about the thing that they asked was changing, right? The question was, how fast is the volume of the cylinder changing? So I also thinking, really, I need to ask, okay, what's dV dt? That's what I wanted. And now I can find the equation relating these 1 to 3 non-time variables. For a cylinder, the volume of a cylinder is the base area, which is just the area of that circle, r squared, times the height. That's your volume of your cylinder. Now, a lot of times, like when we talk about a cone in a minute here, you'll do a thing where you try and eliminate one of these variables, because it'll only tell you that you know how fast like the height is changing and not the height and the radius. But here, since we're being told how the radius and the height are changing, we can just throw the product rule at this. So I'm going to take the derivative of both sides by doing the product rule. So on the left, I'm just getting dV dt. And if you have something by itself not being squared or whatever, its derivative is just its derivative, right? There's no surprises there. On the right-hand side, I have to take the derivative of pi times r squared h. I would leave the pi out as a constant and then take the derivative of r squared times h using the product rule. So the derivative of r squared is going to be 2 times my stuff times the derivative of my stuff times h plus, now we leave the r squared alone, and the derivative of h is dh dt. Now I think we can plug in for all the unknowns and find dV dt. Let's do it. dV dt is going to equal pi times, let's see, 2. So let's see what we've got here. The radius is 5 feet. Be 2 times 5 feet times dr dt, which is 3 feet per hour, times h, which is 4 feet, plus r squared, which is going to be 5 squared, times dh dt, which is negative 2 feet per hour. Now, just to point out, I didn't write any units here, but it's still going to turn out to be right, because here we have 2 times feet per second times feet, which will give me feet cubed per second. And here we have feet squared times feet per second, which will give me feet cubed per second. And we're talking about how the volume is changing, so it should be your unit of measurement cubed per second. But I don't think you need to write that out. You can just add it in at the end. So here we get something terrible. Let's see, 2 times 5 is 10, 3 times 4 is 12, 10 times 12 is 120. So you get pi times 120 minus 25 times 2 is 50. So end up with 70 pi cubic feet per hour. Sorry, I said per second earlier, apologies, per hour. Cool. Question. All right. Still we have to talk about the other things here. So let's do one, maybe two more. So let's do a water tank one. Water tank, shape of a cone. Shape of an inverted cone, I should say. Like an ice cream cone, the point is down. Whose overall radius is 4 feet. Overall height is 12 feet. Is being filled at a rate of 3, let's not use 3, let's use 8 feet per second. 8 what per second? Do my units make sense if I'm filling it with water? Water we usually measure in terms of volume. So really that should be 8 cubic feet per second. Right, we're talking about how a volume is changing if I'm filling it with water. When the depth of the water is 5 feet, how fast is the water level rising? This one again, draw a picture. Here's my conical tank. A pretty good cone. Sometimes that cones are not so good. And we know that the radius of this cone is 4 feet. And the height of this cone is 12 feet. I would probably actually write that to the side. And we're filling it at a rate, well, I guess I don't know, like, I mean, you could be like, yeah, I'm filling with water. There's a big old spigot. Water coming in at 8 feet per second, 8 cubic feet per second. A lot of water. A cubic foot of water. Yeah, okay. Anyway, sorry. So, oh, and then I need to label the things that are changing. So here, right, we've got the water level right there. And we have both the height of this water level, which is going to be changing because we're filling it with water, right? It's going up and up and up. And also, even though we don't really want it, the radius of this is also going to be changing. I'm going to call it R. So here's what I've got so far. Step 1, drew a picture. Step 2, what's changing? Well, I know that dH dt is what I want to find. And I wrote that first because I don't know. I usually wouldn't have written that first. I just happened to write it first. What I would have written first is dV dt, the rate of change of volume, is 8 cubic feet per second. And I want to know dH dt. And they didn't say anything about dr dt in this question. No one is asking me what it is. Nobody's telling me what it is. I'm not going to write it down. I don't need it. We'll get there in a second. So then we need our equation relating our height and our volume. Unfortunately, the only equation that really works for the volume of a cone is the equation for the volume of a cone, which is volume equals 1/3 pi times r squared times h, which has r and I don't really want it. So this particular cones usually require an additional step, which is that we have to figure out how the radius and the height are related to each other. And it's actually really easy with practice. If you look at the big cone, What's the radius? What's the height? And the radius is what fraction of the height? Yeah, the radius is 1/3 the height. Say it again. The radius is 1/3 the height. Oh, so you mean the radius is 1/3 the height? I really do. Now you can do more work here if you want, but it always works that way. The work that we're actually doing that I didn't write down is we're really using similar triangles. If I look at this right triangle here, which has a length of 4 here, a length of 12 here, and then the smaller triangle that's similar has a length of r here and a length of h here. I can say, well, this side is to this side is as this side is to this side. And I can multiply both sides by h and say, oh, great, r equals 4/12 times h, or in other words, r equals 1/3 times h. It totally works. But you don't really, in my opinion, have to write all that down to be able to see, oh, well, this radius to this height is the same as this radius to this height. So your radius is really just 1/3 the height, or whatever fraction you happen to have for your problem. So then we're going to take that radius equal to 1/3 the height and plug it in. And you almost always, I don't want to say always, someone could ask you how the radius of the surface is changing, which seems like a weird question. Usually in this sort of cone-shaped question where you're filling it with water or draining the water from it, they're usually asking you how fast the water depth is changing. So here I would rewrite this as step 3a, volume equal to 1/3 pi times 1/3 h squared times h. I don't want to use the product or the chain rule here. I guess I'm going to have to chain rule really, but I'm going to simplify this before I differentiate either side. So I'm going to get volume equal to 1/3 pi times 1/3 h quantity squared is 1/9 h squared times h. And then one more step of simplification. 1/3 times 1/9 is 1/27. 1/27 times pi, and h squared times h is h. And now we're finally ready to take the derivative of both sides of this. Let's do it over here to save ourselves some room. So then step 4, taking the derivative of both sides, you get dv dt on the left, and you get 1/27 times pi, and the derivative of h cubed is 3 times your stuff squared times the derivative of your stuff. Almost always when you know, I really want to strongly say always. Pretty much always when you do this, the derivative you're trying to find and the derivative you already know should show up in your derivative. So if you take the derivative of both sides and the thing you want or the thing you know aren't showing up, usually means you've maybe missed. It's potentially possible that's not always true, but it's almost always true in these problems. So you should be looking for those things. Finally, plug in. So I know that dv dt is equal to 8. It's equal to, I'm going to write this as 3/27, which I'll reduce to 1/9 in a moment here, times pi, times the height was 5 feet, or the depth was 5 feet, and dh dt. And then this just becomes kind of gross to solve, right? You could write it as 8 divided by all of this. I would probably try and make it look a little bit nicer and say 8 equals, let's see, that's 1/9 times 25, so 25 pi over 9 times dh dt. That's going to give me that dh dt is equal to 8 times 9/25 pi, or 72/25. And my units are, well, since I'm talking about how the height is changing, it's going to be in feet per second. And just to be clear on the work I did here, right? I know I went a little fast there. What I really have here is 3 times 25/27, and 3 times 25/27 reduces to 25/9. And then there's a pi there still. That I feel like I see a few question marks on faces out there. Is there anything else I can clarify here that I've done? Yeah. Because the highest height of the cone is 12 feet, but the question was when the depth of the water is 5 feet. So not when the water's gotten all the way to the top, but when the water is 5 feet deep, how fast is the water level rising? So when the water is 5 feet deep, when the water is 5 feet deep, the H value is 5. Yeah. The 3 came from, so it came from right here. So I have the 3 times 1/27. And I'm just writing that as 3/27. Yeah, totally. Yeah. Because what's 3 really is a fraction? 3 is 3/1. And 1/27 times 3/1 is 1 times 3/27 times 1. I mean, they're all connected via multiplication. And the thing is, when we multiply stuff together, pick whatever order you like. You can do multiplication in whatever order. And I'm picking the order I like, which is I want to write 1/27 times 3 as 3/27. And I can. But yeah, definitely when you're multiplying a bunch of stuff together, do whatever makes the most sense. Like the other problem where, I don't know, it was way back here when I did like, I think it was like the first problem. Somewhere. Now it's disappeared. Sorry, we'll never find it. It's gone forever. Yeah, this one here, when I was doing like 2 times 5 times 3 times 4, and I did 2 times 5 is 10 and 3 times 4 is 12. I could have done whatever order I wanted. I could have said 4 times 5 is 20, and 3 times 2 is 6, and then 6 times 20 is 120. Right? Any order of multiplication, always good to go. Which is nice. Okay. Yeah, all right. We should, as much as I would, one more related rate problem. I did chain rule h because, right, I took the derivative of h cubed, and its derivative was 3 times h squared times the derivative of h. Right, whenever, and pretty much whenever you're doing related rates, rare exception, you're usually doing chain rule somewhere. Because you usually have like your h cubed or your r squared or something. I didn't do it on the left-hand side, right? Because the derivative of v is just the derivative of v. But yeah, usually you're using the chain.
For the radius, like to find the radius, do we have to draw the picture and then find it?
You don't have to draw the picture.
It's just like the number in front of pi and
so this not so there's a coincidence here. So just as let's say we did the same exact problem, and just to change it up a little bit, let's say we have the same problem, but now my cone looked like this, where the overall radius of the big cone was 10 feet, and the overall height of the big cone was, I don't know, do I want to make it annoying? No, kind of 70 feet. And then I had water, and the whole thing was rising, and I wanted to find out, I just wanted to get to the part where I was writing the equation. Well, I would be still writing volume equals 1/3 pi r squared h. But now if this is my radius and this is my height, what's the relationship between radius and height now? Well, what fraction of the height is the radius? 10/70. That's all you have to say. So the radius is literally 10/70ths of the height. Or more easily, the radius is 1/7 of the height. And that is what we're going to plug in right there. So we would say that the volume is equal to 1/3 times pi times 1/7 times h squared times h. And if we multiply it out, it's a little bit terrible, but you get 1/3 times pi times 1/49 times h squared times h. And then 1/3 times 1/49 is something. I think it's 147 times, but let's put the pi on top because we can, and then you have h cubed. So that's how you're getting the relationship by just saying this is to this as this is to this. Yeah, and I think that's a good place to, as much as I could talk about this for the rest of the class, we should talk about the other thing which we haven't talked about, which is going to come on there's one of the, there's so many things. Okay, anyway, we can do it. So the other thing I want to talk about briefly is linear approximation. and I guess I should say linear approximations as well as quadratic approximations. So I will point something out about linear approximations, and then I will tell you how we do quadratic, because it's really just something you memorize. So here's the gist of what we're trying to do. I would like to be able to use a linear approximation. When you see those words, what you should really think is, oh, they mean a line. Use a line to approximate the function f of x equal to the square root of x at a equals 49 to estimate the square root of 51. What's the square root of 49? So I would expect my answer for the square root of 51 to be bigger or smaller? Definitely bigger, right? 51 is bigger than 49. Square root of 51 is going to be bigger than the square root of 49. Okay, but here's the idea of what's happening here. I really would like you to see the idea. So here's my square root function drawn not well. Fine. And right here, let's say this is where 49 is. And if this is the square root of x, we know that the square root of 49 is 7. For here, we have the value of 7. And the idea is, we would really like to know, and I'm going to go way over here, even though I know this is not at all the scale. Over here at 51, we would really like to know what the square root of 51 is. But we don't, and we're not going to. We are going to approximate it, and here's how. At 49, we're going to draw the tangent line. We're going to find the equation of the tangent line, and then we're going to say, well, if I plug in 51 to that tangent line, I get out something not too far away from the actual square root of 51. So right there, that number there, sorry, this is root 51 right here. That number there is going to be our approximation of the square root of 51, which is also called the linearization. So here's the real thing we're doing. We're going to find the equation of this tangent line. We've already done at least 10 times in this class. Maybe that's maybe like 4. And then we're going to plug in the value that we like. So let's do it. All right, so let's see. So I have to find the equation of the tangent line. To find the equation of a line, we need 2 pieces of information. We need a point and a slope. And we already have half a point. I actually have the whole point. What's our point of tangent C? Thank you so much. Slope, we have to use the derivative for. Slope, we're going to find f prime of x. Actually, I should just say f prime of 49 and plug in 49. Let's see, my function is x to the 1/2. My derivative is 1/2 x to the negative 1/2. I might prefer to write this as 1/2 times the square root of x. If I plug in 49, f prime of 49 is going to be 1/2 times the square root of 49, which is 1/2 times 7, which is 1/14. Great, I got my point, I got my slope. So now I'm going to write the equation. Here's my equation of my tangent line. It's going to be y minus the y coordinate equal to my slope times x minus the x coordinate. Or as I might prefer, and you do prefer in this case, if I isolate y, I'm not actually going to write it as y equals mx plus b. I'm actually going to write it as y equal to 7 plus 1/14 times x minus 49. And then often people like to call this L of x instead of calling it y. So I'm going to say that the first order linear approximation, or the linearization, L of x is equal to 7 plus 1/14 times x minus 49. Or more generally, L of x is equal to, well, 7 is my f of a, right? If a is 49 and f of a is the square root of 49, is 7, there's my f of a. 1/14 is my f prime of a. I'm going to get in my way here. And x minus 49 is x minus a. And that is your general formula for the linear approximation of your function. Now we're not done. You still have to plug in the value. If you need me to clarify something, just let me know. Yeah. Yep. Yeah. Because we want to. Because we want to write this thing as a function of x, and to do that we have to isolate the y. But we don't have to make it like y equals mx plus b though, and we don't want to actually. And the reason why is because if you leave it like this and you don't like multiply the 1/14 through, then when you plug in the value of x that is usually close to the value of a, this becomes small, and you can see it's just 7 plus a little bit, or 7 minus a little bit. So if I plug in 51, then I can say, well, great, the square root of 51 is approximately L of 51. And that's going to equal 7 plus 1/14 times 51 minus 49. And if I simplify this, 1/14 times 2 is 2/14. So I get 7 plus 1/7. So I guess you could write it as one fraction if you really wanted to. It'd be 50 over 7. I don't think that really tells a better story, though. I think seeing 7 plus 1/7 is the nicer answer. Okay, so we're gonna use this example still, but I want to go to the side for a second and just tell you what the linear and the quadratic approximations are. So the linear approximation of f of x at the point a comma f of a, or some people might say at x equal to a. They might just say that, and then you have to find f of a. They might not even tell you where to do it at, which is harder, but not impossible by any means, is what we just wrote down. L of x is equal to f of a plus f prime of a times x minus a. A is the number that you're actually using. X is the variable that you're going to plug in for at the end after you've done everything else. And then to go along with that, linear approximation, I should finish my words there, sorry. The quadratic approximation is the same first two pieces, and we're going to add on a third piece. Oh, sorry. Yeah, you guys would tell me if you couldn't see it. So it's going to be Q of x, I think is the notation she's using in class, is f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a squared. And I will tell you all, although you don't need to know this, this is just the beginning of a pattern. You could find the cubic approximation by adding on the next term, which would be f triple prime of a divided by another number times x minus a cubed, and so on and so on and so on. It wouldn't be divided by 3, though. It's actually divided by 3 factorial, which is 3 times 2 times. But it's not important because it's not. So we're not going to derive this from those times. So if I wanted to find the quadratic approximation of this previous thing, well, the quadratic, and it's going to get ugly, approximation of f of x equal to the square root of x at a equal to 49. Well, we already found the first two pieces, right? We know that f of 49 is just the square root of 49. which is 7. And we found that f prime of x was 1/2 x to the negative 1/2, and that f prime of 49 ended up being 1/2 times 49 to the negative 1/2, which is 1/14. And I would encourage you, when you have to find this quadratic approximation, to find these first 3 derivatives, or the first 2 derivatives. I think that's the easier thing to do first. And then f double prime of x is going to be, okay, 1/2 times negative 1/2 is negative 1/4 times x to the negative 3/2, which I might rewrite as negative 1/4 times x to the 3/2. And it's not going to be pretty. It's usually not pretty. If you plug in 49, f double prime of 49 is going to be negative 1/4 times 49 to the 3/2. Usually this can be simplified, but it's often kind of gross. I will point, this ends up being negative 1/4 times. So when you do 49 to the 3/2, what's 49 to the 1/2? And then we do 7 cubed, which is not nice. It's 340. Okay. And I don't know what 4 times that is. So here's what we've got. We've got that our quadratic approximation is going to be f of a, which was 7, plus f prime of a, which was 1/14 times x minus a, x minus 49. I always make that mistake. Terrible. You're plugging in the a value, not the f of a value. And then finally, plus f double prime of a, which is negative 1/4 times 343 divided by 2 times x minus 49 squared. And then if you wanted to find the approximation at 51, or you would say, okay, well, q of 51 is going to be 7 plus 1/14 times 2 plus, I would really say minus, I guess. I'm going to try and make this look less hideous here. So I'm going to write, I know that if I have a fraction divided by 2, it's really just this fraction times 1/2, or 1/4 times 343 times 2 in the denominator. And if I plug in 51 here, 51 minus 49 is 2, and 2 squared is 4. So I can cancel that and that. So I can say, great, my estimate here, and I'm not going to simplify much. I'm going to say it's 7 plus a 7th minus 1/, okay, I can multiply that by 2 and get 686. How terrible. I would like to imagine the numbers on your actual exam will not be this gross. Okay, the last kind of question surrounding this, and I wouldn't know how to do this if I hadn't seen your practice exam. It's asking you, I think, like, in fact, let me grab one of the practice exams. You might as well. Let's see here. Sorry, 1 second. So she says, right, like use linear and quadratic approximation to estimate the square root of 4.2. Estimate the error of the linear approximation. So here's the thing. This quadratic approximation is a better approximation. It's also literally the same as the linear approximation, but with another piece. This next piece here is an upper bound for how big the error can be of this, because you can only be off by at most this much. Kind of neat. Am I saying the right thing? Yeah, I'm saying the right thing. Yeah. So what we can say here is that your linear approximation, the error is less than or equal to the absolute value of this term. Now I will point out a couple things. One, double check this with her. 2, I think I saw an error in at least one of her solutions where she was saying the error was 0.05 squared times, or sorry, divided by 4, and then she said that was 1. That's not 1. It's actually much, much smaller than 1. So I would encourage one of you at least to ask her about that, because it seems wrong to me, and if she thinks it's right, we could have an issue. So, or get her to explain why it's right and tell me why I'm wrong, but I don't think I'm wrong. So yeah. Let's look at least 1 or 2 more examples. Let's see here. Let's do something a little more interesting than square roots here. And actually, let me, yeah, that's fine. That's good. Okay. Let me make sure I'm not doing one she's already done. Because I don't want to repeat the ones that are in the practice exam. Sorry. Give me 1 second here. Make sure I'm not doing something she's already done. Sure, cool, that's good. Yeah, oh yeah, we'll do it that way. Yeah, that's fine. Ooh, arctangent, gross. Yeah, cool. All right. So let's say we want to give a quadratic approximation of 1.98 to the 4th power. Oh, sorry, thank you. Good call. Let me refocus on this part. And tell me an upper bound for the error in the linear approximation that we're not going to ask for. I'm still going to say what it means. Okay, so unlike the previous question, I've not really told you much of anything. I mean, I have, it's just hidden. I didn't tell you what the function was. I didn't tell you what the value was. Often it is your job to find this. So it's really easy to do them. All you do is you take the thing you're trying to approximate and replace the number that's in the function with x. So instead of saying I have 1.98 to the 4th power, I should really say I have, oh, is it x to the 4th or is it 1.98 to the x? Which number seems more terrible to keep? Yeah, 1.98 is terrible. I don't want the 1.98. The number that's kind of terrible, that might be close to a number that's nice, is the one that should get replaced with x. So the function we're actually going to use to approximate 1.98 to the 4th is x to the 4th. Now, no one has told us this either, but what is the nice a value that we're going to use that is close to the value we just replaced? Right. It should usually be pretty obvious. If you're talking about a square root function, like when we were, if I said approximate the square root of 51, you'd be like, well, the closest nice square number is 49. Or if I said approximate the cube root of, I don't know, 65, oh, the closest nice cube number is 64. So usually it should be pretty close to something that's relatively easy. All right, so then if we're doing the quadratic approximation, we need both the first derivative and the second derivative. So my first derivative is going to be 4x cubed. Numbers might get kind of big here. Oh, well. My second derivative is going to be 12x squared. And then we actually have to plug in a as well. So f of a is going to be 2 to the 4th, which is 16. And f prime of a is going to be 4 times 2 cubed, which is 4 times 8, which is 32. And f double prime of a is going to be 12 times 2 squared, which is 12 times 4, which is 48. Awesome. If it were me, I would write down the formula if you didn't give it to me. So I'd be like, okay, I know that q of x is f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. The power of x minus a goes along with the whatever derivative you're on. So first derivative, you get x minus a to the first. Second derivative, you get x minus a squared. I guess if you really want to, you could also say the 0th derivative, you get x minus a to the 0th, which is just, I'm not going to write that down because that's too silly. All right. And now we just literally toss everything in. Oh, yeah, we toss everything into the formula. So my quadratic approximation here is going to be f of a, which is 16, plus f prime of a, which is, where'd you go? 32, times x minus a, which was 2, plus f double prime of a, which is 48, divided by 2, times x minus a squared. Oh, it should be x minus 2 squared. Sorry about that. You should not simplify this at all. Not in your interest. That's okay. I take it back one. I take one tiny piece of that back. You could, if you really wanted to, all right, this is 16 plus 32 times x minus 2 plus 24 times x minus 2 squared. You shouldn't do anything else. Because now what we're going to say is 1.98 raised to the fourth power is approximately q of 1.98. And then I'm just going to substitute in 1.98 for each of the x's. I'm going to get 16 plus 32 times 1.98 minus 2 plus 24 times 1.98 minus 2 squared. I assume you don't get a calculator on this exam. Correct. Okay, so be a little bit careful here, but not too careful. 16 plus 1.98 minus 2 is negative 0.02. And 24 times negative 0.02 squared. Okay, on an exam, you should probably just leave it like this. Or maybe not even go that far. Yeah, I really don't want to do any more work than this. Like I don't even want to do any more work to make you think you should do any more work. I think you should stop there. If you're at, because I mean, yeah, it's not simplified, but okay. And then, and just to point out, just so you all know, this would be your linear approximation. 16 plus 32 times negative 0.02, which would be 16 minus 0.64, if you really wanted to do it that way. Right? This would be 32 times 2 is 64. 32 times 0.2 is 6.4. 32 times 0.02 is 0.64. It's minus. If you really wanted to, you can say the linear approximation is 15.36. Not that we were asked for that. I just want to show it to you so you're seeing it. Okay. So then if we said, well, what's the maximum error of our linear approximation? That. Maximum error. So the maximum error or the error bound should always just be however the absolute value of this last term here. Here it's already positive, so we can just say it. But here our error bound is going to be 24 times negative 0.02 squared. Absolute values if you really feel like you want, but it's already positive. And I guess you can multiply that out. Okay, so if you really felt like you had to multiply this out, what's 0.02 squared? How many zeros after the decimal? Is it 2? I really don't know. Like I know I just asked the question and I should know the answer to. I'm terrible at multiplying decimals. I feel like is it 2? Let's see. Well, let's see. 2 times 0.02 should be 0.04. Right? 2 times, I think it's going to be 3 decimals. 2 times 0.02 is 0.04. So 0.2 times 0.02 should be a tenth of that. And 0.02 times 0.02 should be a tenth of that. So it should be 0.0004. I think like you add the number of decimal places together. Like it's 2 decimal places here, 2 decimal places here, so it ends up in the 4th spot. Honestly, I'm terrible at it. I'm not going to lie. And then 24 times that, 24 times 0.0004. Well, 24 times 4 is 96. So 24 times 0.0004 is 0.0096. Again, I strongly encourage you all to ask her about this because she made what I think is a mistake on one of those ones where she said 0.05 squared divided by 4 is equal to 1. Someone should ask her to make clarify. All right, question.
You identify that the first half is L 1.98.
Well, because we're really like, if we go back to the formulas for the linearization, the linear approximation of a function is f of a plus f prime of a times x minus a. And the quadratic is literally the same first 2 terms, and then we just add on this next piece here. And so if you're talking about how much error this piece could have, well, since this is a better approximation, this amount that we're adding or subtracting on is getting us that much closer. And so this is the most that error could be. It's nice. Okay. We'll do more of these on Thursday, but I do want to give you one more thing because I feel like I should give you one more thing. So I guess you're also going to see on your exam to show that an equation has exactly one solution. Seems pretty likely. Unique, what's that? Yeah, unique root. So I'm going to show, let's make it something terrible. Sure, fine. Show that x to the fifth plus 2x equal to, I don't know, 1 minus x cubed. Yeah, that seems real awful, James. Has exactly one root. Let's make sure I'm not making up something stupid. Let me think for a second. Yeah, that should be fine. Okay, yeah. So first and foremost, bring everything to one side. So we are going to show, and you will probably have to write some amount of words for this kind of problem, that x to the fifth plus x cubed plus 2x minus 1 is equal to 0 has exactly one solution, or one root. Whatever words you want to use, you can use those fairly interchangeably. So whenever you're trying to show there's exactly one of something, you have to show that there is at least one, called the existence part of the proof, and then there is can't be two, the uniqueness part of the proof. So the existence part of this kind of problem typically relies on using the intermediate value. Although technically, you really wanted to be kind of whatever about it. You could say, well, this is an odd degree polynomial. And odd degree polynomials have a range that goes way down to negative infinity and way up to positive infinity. So it has to cross the x-axis somewhere. You could do that. It's not wrong, but it's probably not what you want to do. There's more than one way to solve the problem. But what you should really do here is you should say first off, this function, and I do recommend calling this f of x, or whatever letter you. First off, f of x equal to x to the fifth plus x cubed plus 2x minus 1 is continuous everywhere. So you can say continuous everywhere or on negative infinity. I would probably just use the word everywhere first. Great, we need that because it's a requirement of the intermediate value. 2, second, you have to find two different values of x that when you plug it in, the function is positive at one of them and negative at the other one. I would always recommend plugging in 0. 0 is a great choice. Yeah. So f of 0 is going to be 0 plus 0 plus 0 minus 1, which is negative 1, which is negative, in case you didn't know. And then pick any other number. You could pick, she picked something ridiculous like 1,000. I would go maybe like 1 or 2, or whatever you want's fine. If I pick, let's pick 2 just for fun. F of 2 is going to be 2 to the fifth plus 2 cubed plus 2 times 2 minus 1. And I don't really want to know what that is. And you know what? I don't even know what that is. I know that that is for sure positive. And then I think you actually need to write these next words. Sorry, let me zoom in a little bit. So people have a hard time seeing what I'm writing here. A little too far zoomed in. Sorry. There we go. So I feel like these next words have to appear somewhere on this part. By the intermediate value theorem, there is a solution or root to f of x equal to 0. And if you want to be fancy about it, you could even say where it lives. It's between 0 and 2, or whatever the x values you happen to pick for. Or if you want to say, you could say between 0 and 2, or you could say in the interval 0 to 2. If you want to say it that way. But that's what the intermediate value theorem says. It says if your function is continuous and you go from a negative value to a positive value, you had to have hit 0 somewhere in between. So picture-wise, if you like, you could say, well, look, James, f of 0 is -1, f of 2 is some big number. So from here to there, since the function is continuous, it can't help but cross the x-axis and get a root. Do we know what the root is? No. Do we have to find it? Also no. You never have to find this root, right? When they say show there's exactly one root, they don't mean find the root. They mean just prove to me that there is one, but you don't have to find it. You're not supposed to find it. I don't think we can find it. All right, so then that's the existence part. Oh, yeah, there is a solution. Great. There is a solution. There could be two. And there are other ways to do this, but I guess I should do information. There's a fancier way of doing it, but we don't need to be fancy. So what I assume is going to happen here is your function, its derivative is always going to be positive or always going to be negative. I would be willing to bet, since most of the examples I've seen are positive, I bet she's going to make it negative. I would be willing to bet the derivative of your function will always be negative. But we'll do one like that on Thursday. But here we take the derivative. It's equal to 5x to the fourth plus 3x squared plus 2. And if all the powers are even, that means when you plug in either a positive or a negative value for x, those are always going to spit out positive things. Or I should say non-negative things, because technically if you plug in 0, you can get 0 plus 0 plus 2. But no matter what you plug in, 5x to the fourth is greater than or equal to 0. 3x squared is greater than or equal to 0. And 2 is equal to 2, or greater than or equal to 2. And so this derivative is always greater than or equal to 2, which is positive. Plus, since the derivative is always greater than or equal to 2, since f prime of x is greater than or equal to 2 for all x, that means the function is always what? Oh, good question. The derivative is always positive. Right, or if the rate of change is always positive, it's always increasing. That means f of x is always increasing. Which means there can only be one root. Because if you're always increasing, once you cross the x-axis, there's no going back. You can't turn around. Right? I've done this. I have somehow crossed the x-axis, and now I have to keep increasing. Even if I slow it down, I just can't turn around. Right? There's no going back down to the x-axis if you're always increasing. So that's the idea of how we say that this is true. Since the function is always increasing, so there can only be one root or one solution. And I assume that's how she expects you to do it, because I think that's how she's done it in every one of the practice tests. Yeah. No, it's also true if it's only, so that's why I think she's going to do it decreasing, because let's say, for example, just real quick, let's say our function, in fact, you know what you could have done instead? You could have done this problem. Oh, you know what's cool? You could make it so it's always increasing if you want to. Because you could bring, if you're trying to set something equal to 0 and everything happens to be a negative sign, bring it all over to the other side. It's all a positive sign. But let's say we made the choice and brought everything. I'm sorry, let's see that. Let's say we made the harder-ish slightly choice and brought everything over to the right. Then what instead I would have would have been this. I would have had 0 equal to 1 minus 2x minus x cubed minus x to the 5th. I could still show there's one solution, or there's a solution between 0 and 2, right? I could say this is my g of x, g of 0 is 1, g of 2 is 1 minus 4 minus 8 minus 32, which is definitely negative. That shows there is a solution. So existence, check. And then, of course, you should write more words. I'm just doing it fast because it's literally 259. And then second part, g prime is equal to 0 minus 2 minus 3x squared minus 5x. But again, we have all even powers. So x squared is always positive, but negative 3 times a positive is always negative. And x to the 4th is always positive, but negative 5 times that is always negative. So here what we could say is this is going to be less than or equal to negative 2, I guess minus 0 minus 0. So this derivative is always negative. And if your function's always negative, sorry, if your derivative is always negative, that means your function is always decreasing. So if we're always decreasing, instead of going up from left to right, we're going down from left to right. So we go down, down, down from left to right, we cross, and then once again, there's no getting back up over the x-axis, right? We have to keep going down from left to right because we are always decreasing. If I turn around, I've broken the rules. Now I'm increasing. That's not allowed. We said the derivative was always negative. Right here, the derivative would be positive. No, that's the whole point. If she asks you to show it's unique, she has to give you a function where it's going to be unique. So, right, we can't, like, if I give you a function where this didn't work, the answer would be we can't do it. So for us to show this function has a unique zero or a unique root or solution, whatever you want to call it, it's going to be something where the derivative is either always positive or the derivative is always negative, because in that case, you only get one root because you cross and you can't go back. Yeah. There are plenty of functions that have multiple roots, just not these ones we're looking at, because we're being asked to show something.